So you type a prompt into ChatGPT, hit enter, and boom, the magical text just starts streaming back to you. We've all done it. But have you ever wondered what actually happens in that exact second after you hit enter? Because beneath that super clean chat interface is a back-end solution that is just unreasonably hard to build. In this explainer, we're going to demystify that magic. We're going to unpack the entire journey of a prompt by looking at the physical hardware and the specialized software powering the whole shebang.
Okay, let's dive into this. Right now, tech giants like Amazon, Google, Microsoft, and Meta are collectively spending over $700 billion. Yes, that is with a B, on AI infrastructure this year alone. That's literally 4 times what they were spending just 4 years ago. And to put that into perspective, McKinsey expects close to $7 trillion to pour into data centers by 2030. Think about that for a second. Somebody actually has to build all of that and keep it running. To understand exactly how they pull this off, here is our roadmap for today. We'll cover 1. What are AI models? 2. CPUs versus GPUs. 3. The GPU memory bottleneck. 4. Serving models. 5. Scaling infrastructure. And finally, 6. Smart routing with LLM-D. All right, let's kick things off with Section 1. What are AI models? From simple math to the transformer. Beneath the sleek chat interface, the model doing all the heavy lifting is ultimately just a giant math formula, specifically a transformer. You can kind of think of it like a simple doubling machine. You drop in a number, let's say a 3, and a 6 comes out. It doubles it. The formula is just the structure: input, multiply, output. But the specific number hiding inside that makes it double, that times 2, is what we call a weight. In massive language models like GPT, Claude, or Llama, the basic formula is broadly the same, but the model has billions of these weights that it learned from reading mountains of training data. To a systems engineer, this advanced AI model is really just a massive file sitting on a disk, completely packed with billions of numbers, just waiting to be poured into a formula to do some math. Moving right along to Section 2, CPUs versus GPUs. Why a regular processor just isn't enough. So if a model is essentially just a giant file waiting to do math, why can't we just run it on our laptop CPUs? Well, running a model requires billions of extremely small, independent multiplications that can all happen at the exact same time. And this brilliantly illustrates the core hardware problem. A standard CPU is a brilliant generalist, but it only has a handful of powerful cores meant to do things sequentially, one right after another. If we give a CPU billions of multiplications, you are going to be waiting a very, very long time. A GPU, on the other hand, is built the exact opposite way. It's packed with thousands of small, simple cores designed specifically for massively parallel processing.
Just to give you a real sense of that scale, a GPU can do about 100 times more math per second than a typical CPU. A standard CPU manages roughly 10 trillion operations per second, whereas a data center GPU can push closer to 1,000 trillion operations per second.
Wait, why is this an issue then? If GPUs have all this incredible computing horsepower, why in the world are they constantly starving for data? Well, a processor needs memory to feed it data, and that introduces our next major bottleneck: actually getting those massive weight files from the system memory over to the GPU cores fast enough. Let's look at how we fix this in Section 3, the GPU memory bottleneck, navigating the narrow pipe. Here's the deal. If we leave the model's weights sitting in regular system RAM, they have to travel down a frustratingly slow, narrow pipe to get to the GPU. This leaves our thousands of ultra-fast GPU cores just sitting there, completely idle, waiting for numbers to arrive. The industry's solution to this narrow pipe is VRAM, or video RAM. Instead of the processor and memory sitting far apart across a motherboard, the GPU packs ultra-fast memory directly onto the card, right next to the processing cores. This acts as a massive, wide highway where data travels at terabytes a second rather than gigabytes. So now, the model's weights live right beside the math cores. But the catch? VRAM space is incredibly precious. Just think about how compute power and VRAM capacity scale across hardware generations. An older NVIDIA A100 data center card has 80 gigabytes of VRAM. An H200 pushes that to 141 gigabytes, and the newer B200 boasts 192 gigabytes with a staggering 8 terabytes per second of bandwidth. Literally, every AI workload on the planet is sized by these 3 specific limits: compute, capacity, and bandwidth.
Which brings us to Section 4, Serving Models with VLLM, the prompt's journey.
Okay, let's zoom out from the physical chip to the software server. To actually answer your requests, we use model servers like VLLM, which reads those gigabytes of weights off the disk and loads them directly into that precious VRAM. But once the server is up and running, how does it actually answer you? Language models don't write whole words. They write tokens, which are roughly 3/4 of a word. The model is essentially a predicting machine. It runs a continuous loop. It reads your prompt, guesses the next token, adds it to the text, and runs the entire loop all over again. A 100-token answer means the model ran that exact loop 100 times. And that is exactly why you see the output stream word by word on your screen. Now, this journey is strictly split into two phases. First up is the prefill phase. This is that brief initial pause you experience before ChatGPT starts typing. It processes your entire prompt at once in a massive, compute-heavy burst. Then comes the decode phase. This is the token-by-token loop. For every single new word, the GPU has to read the entire model out of VRAM, making this phase incredibly memory bandwidth heavy. Now, what's really interesting about this setup is the KV cache. If the model had to do that heavy prefill calculation for every single new word, the chat would be hopelessly painfully slow. Instead, the server saves that heavy initial work into a memory scratchpad on the GPU called the KV cache. For every new token, it just reaches into this cache, reuses the work, and slaps one new token on top. This scratchpad is the absolute key to fast streaming. But remember, memory caps everything. A large 70 billion parameter model is about 140 gigabytes in size. So what exactly happens when that massive model simply does not fit onto a single 80 gigabyte GPU? That brings us to Section 5, Scaling AI Infrastructure. From single GPUs to massive clusters. To serve these giant models, or honestly, just to handle thousands of users at once, we have to zoom out again and connect multiple machines together into massive clusters. We solve the fitting problem using a really clever technique called sharding. We take the giant model, slice its layers into pieces, and put one piece on each GPU. No single GPU holds the whole thing, but together they act as one logical server. If they're in the same box, they talk constantly over an ultra-fast internal cable called an NVLink. If they're across different machines, they talk a bit more lightly over the network. But here's the kicker. When we scale up to an entire fleet of these servers to handle global traffic, standard web load balancers completely fail. A traditional load balancer spreads traffic evenly, treating all servers as perfectly interchangeable. But remember our precious KV cache? If a standard balancer sends your second message to a random new server, that server has to recalculate everything from scratch, literally throwing away the saved work sitting on your original server. We absolutely need cache-aware routing. And that leads us to Section 6, Smart Routing with LLM-D, the fleet brain. The industry hit this routing wall hard, which is exactly why tech giants like Red Hat, Google, IBM, and NVIDIA teamed up to build an open-source solution called LLM-D. It operates right on top of Kubernetes, which is the platform most organizations already use to manage their workloads. You can think of LLM-D as the brain for the entire fleet. When a request comes in, it stops and thinks before it acts. It keeps track of exactly which server holds your saved KV cache and routes your follow-up questions straight back there, entirely skipping the massive reread. This trick alone can give up to 3 times the throughput. It also physically checks real-time memory availability and queue links inside the servers, ensuring your massive 50-page prompt doesn't overload a server that's already busy streaming answers to 30 other people. So the crucial point is how LLM-D uses a concept called disaggregated serving. This just means it physically splits the fleet into 2 separate pools to handle those totally different hardware requirements we talked about earlier. It sends the compute-heavy prefill phase to a pool of GPUs fully optimized for calculation, like H100s. Once the prompt is read, it hands the saved work over a fast link to a memory-heavy pool, like H200s, dedicated solely to the token-by-token decode streaming. Each pool runs on the exact hardware that perfectly fits its specific job. As we wrap up this explainer, it's vital to realize that beneath the magic of generative AI is an absolute masterclass in systems engineering. From managing memory bottlenecks on the physical GPU card to orchestrating complex Kubernetes deployments and routing rules with LLM-D, these are the real backbone of AI. As the source material points out, the hard problems in AI are infrastructure problems now, completely empowering DevOps and systems engineers to take the lead. We've journeyed all the way from a single math equation to a globally routed, cache-aware fleet of supercomputers. But honestly, this is just the beginning. As AI data centers continue to absorb trillions of dollars, how will our physical infrastructure evolve to handle the next generation of trillion-parameter giants?
It's a fascinating challenge, and understanding these foundational building blocks is the first step to being part of the solution. Thanks so much for exploring the journey of a prompt with me today.